Hello, everyone. Welcome to the second part of the CiA Technology Day. My name is Mariam Khaghani. Uh, I would like to today present about the theory generation of CAN. This is my educational background and also the current position in the CiA office. I work here in as technical manager of CAN in Automation GmbH. Uh, this is my agenda of my presentation. I would like to start with a brief overview on CAN evolvement. In February of 1986, Robert Bosch and Intel announced that the companies are jointly developing a high-speed communication link for interconnecting electronic control units in the automobiles. They called it controller network area network, and I'm sorry, and it is the famous CAN. In 2012, Bosch, with cooperation with the car makers and other CAN experts, introduced CAN with flexible data rate, or the CAN-FD. The main reason of this introduction was to communicate with a higher bit rate and expanded petabyte per CAN. And in 2021, the third generation of CAN and CAN extended data feed length, or CAN-XL, was specified by CiA CAN-XL Special Interest Group. Over the time, electronic control units were introduced step by step and more, and which were connected to in-vehicle networks. Most of them were connected to a CAN-based networks, but there was also the coming after other networks such LIN and FlexRay. Starting gathering these units in a vehicle caused some chaotic network architectures. So there was a new approach on that time. The name was domain-oriented system. It was a good idea because you could simplify the system by their function, but in different part of a vehicle, that's unfortunately these networks have the different components and of the different domains which are located in the different parts of a car. It means that there was a lot of necessary cabling with increasing number of the ECUs. It was also not very convenient, in particular if you want to save weight, and of course the cable means weight. So there was a next idea, zonal architecture, which is more regular network approach. In comparison to domain-oriented approach, zonal architecture classifies ECUs by their physical locations inside the vehicle. It means each zone has its own ECU. For this future architecture, we need some requirements, of course, and one of them is the network scalability regarding bitrate, data length, due to the fact that there are different subzones such as sensor actuators with different bandwidth. We need this requirement. And another requirement is integration of legacy approaches. This means we need something where we can migrate easily from today's architecture to the future one. And we need also to prove that the devices which we develop are interoperable by means of independent interoperability tests, for example, like FES. And we need also reliable data link layer protocol and robust transmission of signals, which is related to physical layer. Even when we have multiple higher layer protocols sharing the same cable. And because we see that these backbone networks will be Ethernet based, tooling and forwarding of Ethernet frames is needed. And as you can see here, further requirements are needed. In this slide, I would like to talk about CanXL features. And here you can see the features, but I want you to ask yourself why actually we need CanXL. Um, I would answer instead of you because yeah, I can say it helps you to implement a network which has a payload of 2048 byte. And also with the new features like virtual CAN ID, you can run several parallel applications on the same cable. And also with the two CRCs, you can have a more reliable network. And also with the new SDT or the service data unit type, which is similar to the Ether type, it can be indicated which next layer or which protocol has been chosen. And further features, as you can see here in this slide. And to have a direct overview, we see on this slide, there are three CAN frame formats. The principle of the CAN data frames has not been changed so much, as you can see here. These three different generations have almost the same field. And but what is mostly changed is I can say that in arbitration field we have frame priority only. In the control field we have the new SDT, that type of data indication, and also the higher layer function used such as sec, and PCRC virtual network allocation, and also the using address field. We can have ID based and source destination based addressing. Now let's have an in detailed view on the Mac frame in CanXL format. Here we see the OSI data link layer PDU with the new change fields in comparison to CAN-CC and CAN-FD. You can see here we have 15-bit arbitration field, 81-bit control field, and the payload of a 2048 byte data field. And in the arbitration field, we have the 11-bit priority ID that just allocated to the priority and allocated to the priority, and we have 1-bit FD frame format and XL frame format to indicate whether the frame is in FD or XL format. And we have also ADS and DAS fields that which will be used for switching between arbitration phase and data phase. And we have also the 8-bit STT and 8-bit VCID, and 1-bit for the higher level function sec. And I like to be emphasize about on the two CRCs. As you can see here, the CanXL data frame has two CRC and 13-bit PCRC or prephase CRC and the 32-bit frame CRC or FCRC. And these CRCs are cascaded. It means that FCRC protects also the PCRC. And both CRC together are able to detect any 5 randomly distributed bit errors. And it corresponds to a Hamming distance of 6. In this slide, you can see the differences of this three generation of CAN. At first, you can see here theta fin length of CAN XL is much larger than CAN CC and CAN FD. The CAN ID in CAN CC and CAN FD is used for both arbitration and addressing purpose, and they have two options to have 11-bit or 29-bit. But in CanXL, this function is separated, as you can see here. So CanXL protocol has 11-bit CAN ID instead of. And it has a new field named acceptance field, which has 32 bits. ID-based and source destination-based addressing is achievable by this field. This field also contains not address or authentication information like message ID. And the new for only CanXL are 8-bit STT and 8-bit VCID field. The STT indicates the use the next OSI layer protocol, and the VCID field allows you running up to 256 logical networks on one single CanXL physical network segment. Also, there are some changes in pita stuffing, as you can see here, and the CRC, as I mentioned in the last slide. But the CanXL nodes have the ability to be configured by a software error signaling behavior. Therefore, two kinds of setting are available. When the error signaling is enabled, it means that the node behaves like a CanFD or CanCC node regarding the error handling. And when the error signaling is disabled, it means that no automatic retransmission of faulty data frames. That means CAN node is not compatible to CanCC and CanFD. And in a better word, I can say that CAN node supports only CanXL frames in this mode. And as you can see here, the fast mode switching by ADS field is configurable only by CanXL, which is achievable when the error signaling is off or disabled. You can see here in this slide a graph that shows you the ability of tree CAN generation. As you can see here, with using CAN CC and communicating up to 8 byte, you can have a 0.5 megabit per second. And by using CanFD and communicating up to 64 byte, up to 8 megabit can be achieved. And you can see here the great difference between CanXL in comparison to the other generation of CAN that using CanXL and communicating up to 2048 For 2048 byte, up to 16 megabit per second can be achieved. Excuse me. So I would like to mm, mm, talk about the CAN physical layer. Here you can see the four different CAN transceivers. Uh, they are compatible, but under some condition that you need to be aware of the configuration possibilities. We have a CAN CC transceivers that features high speed transmission with non-return to zero coding, and the bit rate can be achieved from 40 kilobit per second to 1 megabit per second, of course, depending on the network topology. And you can see here the CAN-FD transceivers that features also high speed transmission with the non-return to zero coding. And the arbitration bit rate in CAN-FD transceiver is the same as in CAN-CC, and the data phase bit rate is up to 2 megabit per second or higher when you use not optimized network topologies, and up to 5 megabit per second also can be achievable with using two nodes. And you can see here also the CAN-FD SIG or signal improvement capability transmission with non-return to zero coding as well, and up to 8 megabit per second, even when the using not optimized network topologies is achievable. And you can see here the new transceiver, CAN SIG XL, that has two modes, SIG mode and CAN XL fast mode. During the SIG mode, data is transferred using non-return to zero encoding, but during the fast mode, the data is transferred using PWM encoding. In this slide, you can see the flexibility of CAN physical layer design. Using different ECUs and or CAN protocol. For example, here you see using a super speed XL ECU with a CAN XL protocol when the error signaling is off, and also using SIG XL transceiver with mode switching, you can achieve the bit rate between 12 and 15 megabit per second. And also you can see here another example that when using XL ECU and CAN XL protocol, when the error signaling is on, and also using SIG XL transceiver when without mode switching, 5 to 8 megabit per second can be achieved. Here you can see the result of CAN XL plug fest in the last year. As you can see here, it is shown that 20 megabit per second seems to be possible. It's not just paperwork. Actually, using having two nodes using point-to-point topology, and also having eight nodes using daisy chain topology, and also for linear bus topologies with short stops connecting 8 nodes and 20 megabit per second, considering ringing caused by topology is achievable. Now I would like to ask you to imagine you are a CanXL system designer. So you need to know about your benefits, which I would like to name them tools. Uh, and up to 20 megabit per second is in fast mode. Throughput is possible for you. Uh, Extended data field is sufficient space for any content in user defined size. And with VCID, you can have group ECUs to the various application specific. And with using STT, you can have different applitions that may share the same CAN. And using the higher level function, sec CanXL embedded higher layer function, it may assist solving and issues such as security and host load. Acceptance field offers and options for sophisticated addressing, such as signal-based and service-oriented addressing. And with the compatibility of CanXL, you can have mixed CanFD and CanXL networks enable migration paths. Uh, Separation of priority and addressing. As you can see here, we have 11-bit priority ID that allows a focus on the priority, no further functions such as addressing. And with 32 acceptance field is included in the 64-bit hardware acceptance filter of the CanXL controller. It can be used for any type of filtering,
Interesting.
such as content-based and service-based.
ايوه فهمت ايوه.
In control field, the 8-bit STT providing information on the data content is which is similar to Ether type function that indicates they use the next higher layer protocol. Um, by using CanXL, now you can see here that the CanXL until now supports the differentiation of these data contents, such as map, mapping of CanCC data frames and CanOpen and the others. The optional CanSec data link layer security protocol is building block to meet future cyber security requirements. CanSec and frame fragmentation. CanSec is a practical solution to secure the CAN bus against the most common threats facing CAN networks, while reducing host CPU overhead and the demand for larger and powerful hardware security modules. And frame fragmentation enables dynamic bus load control and keeps latencies at the CAN low. In this slide, you can see an example of interoperable CanXL with different network protocol using SDT function. Here, CanXL provides an interoperation between, for example, FCU using CanOpen and FMU and other units. Uh, Now, I would like to tell you that CanXL has been standardized in ISO 11898-1 and -2, and Also, we have many CiA specifications which are under development. For example, CiA 611 series specifies STT types in part 1, and in part 2 it specifies a generic transport layer requirements. And also it has a part 3 specifying generic transport layer conformance test plan. And the other specifications, as you can see here. Uh, this slide shows you that CanExcel is not just paperwork. You can get its products. As you can see here, some companies produced CanExcel products. Therefore, implementation of those products are available. And you can be updated with these products and the Can Excel availability in the Can Excel website that is recently developed by CiA, and especially the cooperation with the marketing group Can Excel. In this website, you can see you can get information about CanExcel features, applications, and physical layer options, and also the hardware, software, and tools, and other products. It is accessible from CiA homepage. Also, it has a direct address, as you can see here. So, as the summary, I can say that CanExcel provides an entire ecosystem for designers, and it is intended to be used as a backbone or sub-backbone network. It also provides not only an high data throughput at a line topology, but it comes also with many higher layer functions that supports the system designers, such as CanSec and SDT. And CanExcel also can be used as alternative lower OSR layer approach for Ethernet-based higher layer protocols. And CanExcel is already available at several sources, as I have mentioned in the last slides. And thank you for listening to my presentation. If you have any question, I would like to answer them.